Yes, sorry. I was hearing myself, I couldn't focus. Okay, so the first one, risk associated with interior low-E coating. This is a research that has been going on for several years, and I really want to draw attention on this specific topic. I think it's something that we will probably be going to hear some consequences of that in near future. So I would like to share that as we go through this path of energy efficiency. So today I'm going to talk about a little bit of a background, what was the drive behind the research, the actual research, next step, and some conclusion. So as you know, the glazing assemblies, windows and doors have the lowest thermal performance when you look at the whole building enclosure. And so there has been a lot of emphasis on improving their thermal performance. Now, obviously, triple glazed, as we know, with two low-E coating, with proper warm edge spacer, thermally broken frame, can offer good performance when it comes to improving the thermal performance. However, there have been some challenges with triple glazed window as far as the weight, the cost. I'm sure how many of you have seen we use triple glazed windows in almost 90% of our engineering projects. The weight, the associated installation sometimes makes it difficult and challenging for the installers as well as for the manufacturer, especially when you're talking about very huge sized doors and windows. And that's why North American window industry, and I would say North American because this practice is not used in Europe. North American industry has started to say, what can we do so that we can still stick with this double glazed, but try to maximize the thermal performance of it. And so what was done was that so the solution was, how about when you get the typical double glaze with one low-E, let's say, so this is surface number 1, 2, 3, 4. So let's say you have surface low-E on surface number 2. You will add an additional low emissivity coating on the surface that you will be able to touch the most closest surface to the occupant. So what happened is that when we're dealing about night, at night there's no sun, nothing. So when is the majority of the heat loss is happening? In the case of no low emissivity coating, when the indoor heat was getting to the glass, was getting absorbed, a good portion of the heat was getting absorbed. As a result, the temperature of the glass was a bit warmer. In this new solution, the indoor heat, again, the heat from the inside, it reaches the glass, but a good portion of it is going back to the room, which is exactly what we want to do. But there is something happening as a result of this. There is a byproduct. Since the good portion of the heat is being reflected back to the room, as a result, it doesn't being absorbed by the pane of the glass, the temperature of the pane goes down. So in this case, center of glass from 13.5 drops down to 8.8. This is not something new. You can just run this through the window software, the term software, and you can get that. So this part is been known to everyone. Now, the advocates of this energy efficiency, when we talk to them, they said, well, Hamid, we understand, yes, we acknowledge that this is happening. But in their opinion, the impact is limited to the center part of the glass. They are of the opinion that the edge, the perimeter edge all around, it's not being noticeably impacted. In other words, sometimes when it comes to discussions like that, they say, well, you know what, if you're concerned about condensation on the edge of the glass, we will have it regardless if such low-E coating was not even present. So then that actually started in 2018. You know, it happens a lot of time that in the past that we get excited about energy efficiency. You know, everywhere you go in, especially I'm from BC, there's quite a focus right now in improving the thermal performance and airtightness, and it's great, it's perfect. But there is a catch. If we don't do it holistically, there is a possible that we start to cause some negative consequences. And for those of you who are interested, if you do some search on thermal performance improvement in all buildings in Europe, they started long time before us. Originally, they didn't do it holistically. Everybody was excited about energy efficiency, but it didn't come in a holistic way. They caused some issue. That's why they stood back. They reflected on the lessons and came up with solutions that result in high performance outcome, not just only energy efficiency. So as a person who has been exposed to that side and this side and the window development, I really thought that this is something that also needs to bring attention in a sense that how that lowering the temperature is going to impact thermal comfort or moisture management. When I'm talking about thermal comfort is that if we acknowledge that the glass temperature is being lowered, now my body as 37 degrees, it's going to have a more net radiation heat exchange with that cold surface. We already know the windows are cold, double-glazed one. That's why we put the radiant floor heatings the baseboard heaters or all of those heat register close to the windows so that we can raise their temperature to help with the condensation resistance as well as to keep them warmer so my body start to do less net radiation heat exchange. But now how that's going to impact, now that we are reducing that temperature, how it's going to impact the thermal comfort as well as the condensation resistance. How forgiving is it going to be in lack of perfection, the occupant use, changes in the occupancy? And especially I started to get involved in projects in a colder part of the BC, especially it doesn't have to necessarily be cold. This one is in Kelowna. They get a lot of cloudless nights where we had doors and windows double glazed with one low E and with two low E. The one with single low E didn't have a problem, but the one with the double low E started to get these sort of issues. So I started to think that, you know what, let's reach out to the manufacturer. Window manufacturer the owner started to get in touch with the window manufacturer, it's a local one, saying that, well, no, we don't think this is the impact of the interior low E coating. Although we had other evidences in that house on similar windows with single low E, no issue, that gentleman was arguing that, no, that's not the case, because if there was a problem, we should have seen condensation on the center. We are seeing it on the edge. And then when the homeowner followed up, this is a homeowner who built the energy efficient house. This is supposed to be a house that is recently built and supposed to provide good performance. Then the homeowner said, you know what, the window manufacturer said, you know what, you're looking for a solution, design solution. I don't think we have a design solution. And when the homeowner said, what about triple glaze? Look at that response down there. It says that I don't think the triple glaze is the solution for you because the triple glaze is going to impact the center of glass, not the edge. And I was just observing this type of discussion. Now, when you look at the low-E manufacturer, the type of low-E that is very common in our market, there is a statement in their website saying, yes, while low-E reflects heat back into the room, the center of glass temperature will be slightly cooler. And they use the word slightly. However, the edge temperature and ultimately the window ability to resist condensation is driven by the performance of the edge. I don't understand what this statement means. Nobody is disputing the fact that the condensation of the whole thing is driven by the edge. We know that. This is the weakest part of the system. The question was this: is this interior low-E coating going to make it even worse? That was the whole point. Knowing that the edge is already weak, are we making it weaker? So far, there hasn't been a research on that. So I really thought that it's important to look into that. But before, I just want to give a little bit of a background. Right now, we are looking at, this is a center of glass value, double glazed with one low-E on surface 2. This is double glazed with low-E on surface 2 and 4. And when you compare the two, the R value all of a sudden bump up from 4.2 to 5.2. So adding that coating all of a sudden adds quite a lot to the thermal performance. And my question for you is that what causes that? When you start to calculate the R value of the center of glass, you know we have a R value for this glass, which is almost nothing. We have an R value for this. And then we have an R value for the aerospace plus the low-E and the gas. There are two more low R values. What are those? Surface films. So surface film on the outside, surface film on the inside. Now in this case, adding that lowy on the inside would result in increasing the surface film resistance to a point that it comes to 31%. 31%, almost 1/3 of the whole thermal resistance offered by this guy is offered by something which is not even part of the glass. It's something that we don't even see. It's caused by surface film. So the question is that, what is surface film? In an intuitive way, what do we mean when we say surface film? Surface film is nothing other than the integration of how the heat, indoor heat, through convection radiation, easily reach to the glass. If the heat doesn't get to the glass as easy as it should, then that means there is resistance. We start to get a lot of resistance, a noticeable resistance. And that's good for energy efficiency. Our R value goes up, everybody's happy. But if the heat gets fast and easy, the heat transfer has happened fast, then there is not that much of a resistance. So now the question is this, now that we know, you may say, well, why are you picking on this? Because for regular walls, typical windows, roof, surface film resistance is the minute in the whole spectrum of the total thermal resistance. So its impact is negligible. Right now we are talking about something which is almost 1/3 of the total resistance. So the question is that, is it really 31%? What about if it's 40%? How is that heat, for example, if we don't, in a real world, we don't deal with IGU. We live with a window inside the wall. But what happens if you start to place a window too deep out versus too deep in? How the heat is gonna get to that glass? You guys, the window manufacturer, all of your analysis, NFRC 100, 200, 500, whatever 100, it's all based on the actual window. In reality, this is what we're dealing with. That the placement of the window inside, if the window go too deep, the heat doesn't get, the recess creates some sort of a blockage for the minimizing the radiation, blocking the radiation. And now the next question is that, what about now you take that wall and install it in a house or in a building in which the heat either have radiant floor heating, means the heat goes from uniformly from the floor, versus baseboard heater when the heat is so localized and has to somehow transfer and get there, versus you do it from the ceiling like here when the warm air has a tendency to stay up. How are these things going to impact that heat transfer and surface film, knowing that surface film all of a sudden is playing a big impact? We're just making an assumption on the term software right now based on a fixed value, but how is this actually translate in real performance of end users' experience? And that is why we started to invest on this type of a research to raise the awareness. We chose two types of walls. One of them was fully exterior insulated concrete wall. A concrete wall, this is a part 3 construction. We see it a lot, especially in BC right now, a lot of all the insulation on the outside and the window moved all the way flush to the inside versus all the way flush to the outside. We also chose a split insulated wood frame wall. We keep seeing that 2x6 or 2x4 added some insulation on the outside. Do the same thing. Put the window on the inside and also put it at the shearing level where the flange is located. Trying to understand. And then next step, what we did, we put this into a building looking at in the concept of 3 different heat sources. Now, not only we have, where is my pen? Oh, it's here. Sorry. Not only we have basically 2 types of walls, we also have different placement. In this case, window inside. In this case, window outside. We also have 3 types of window. One is double glazed with 2 lowy. One is double glazed with one lowy, and the other one triple glazed with 2 lowy. And installed in a situation that it will be exposed to 3 types of heat sources, with the goal to determine the condensation resistance and thermal comfort, trying to understand, and this is something that is missing. The reason I love this study in a sense that it tried to bridge the gap between HVAC and building envelope and architectural, because all of us are so focused on our own discipline. But this one is really trying to connect us and see how the heating system, the placement of the window, the type of the orientation, and the low is going to impact. So we decided to do it in 3 types of phase. Phase 1, CFD, and I will explain to you computational fluid dynamic, why we have chosen to do that and not software that are readily available like term. The second one, experimental setup, building a room with that dimension, with that window, with different walls, and moving this and doing some experimentation and measuring all of that, measuring the ankle draft, the speed, the temperature. So with regards to thermal comfort, there would be some bodies will be there and having some sensors and measuring all of that. And then phase 3 would be case study. It's been an ongoing project. Today, I am sharing with you part of phase 1, which is the computational fluid dynamic. In other words, today I am sharing with you the result of the condensation resistance based on the radiant floor heating when the window is placed on the outside for both wall assemblies based on 3 glazing configuration. In other words, when you look at this guy, we are going with this one. The case of window all the way to the outside, window all the way to the outside based on 3 different type of windows, 3 different type of glazing configuration. Same thing for the wood frame. Same thing for the wood frame. So we're looking at the condensation through the CFD one. And you may say, why CFD? Why didn't you go with term? And there is a problem. And that we originally didn't want to do CFD. We were planning to basically analyze that with term. But once we went deeper into that, we realized that software like term is based on ISO 15099. You guys are familiar with that. And under that, there is some sort of an assumption. Convection heat transfer, not the radiation, the convective component of the heat, how the indoor heat gets to that, it's not thoroughly modeled. It's based on certain assumptions. And it was right so far, because who cares? This is the first time in human history we are using a low emissivity coating with the emissivity of 0.1 or less than that exposed to the occupant. All these products that we are seeing here have the emissivity of 0.9, 0.84, all of that. This is the first time that we are using that. So far has been okay. But right now, we didn't want just some assumption. We were thoroughly looking at the impact of the convection. In other words, we wanted to see how the warm air goes and moves and come in touch with the window, how the interaction between the air on the inside happening with the window. Why? Because that impacts the surface field, and the surface field plays a huge role when it comes to this new technology utilizing North America. In other words, I wasn't looking for this type of output that we see from software like term, but rather see the temperature distribution, not just only on the wall and window, but also across the room. So in other words, having that connection. So case 1, fully exterior insulated on the outside. This is with 2 low E. This is with 1 low E. This is triple glaze with 2 low E. Just pay attention to this slide, okay? Now, you may say, what are these ones? What is this, Hamid? Well, since we are moving all that insulation out, you guys are familiar now, the thermal performance is moved out. You want to place your window as close as possible, aligned with the plane of insulation. So these are the products that are widely used in part of Europe. I really hope one day we can see it, because that makes a lot of job very easy for installation of these windows in fully exterior insulated. Almost all the windows ordered from there comes with this package. Window companies order that. Products that actually offer a very good structure, 500 PSI, at the same time, very good R value, around R3 per inch. So the combination of the two, so you can just bang, 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 connect this, and then sit the window over that. So in other words, we built some of these in our office to just show the intent. This is an exterior insulated wall. This is also an exterior insulated. This is type of product I'm talking about. This is another version. You can also, so this was that project in Kamloops that I was talking about. So you install these, and then by the time you put the insulation, everything would be lined up, warm, insulated, the frame and the edge, everything would be properly insulated. So that was the whole point of doing that. Okay. And then, so we select the room 12 feet long, 12 feet wide, 9 feet high, and the window was 4 feet by 4 feet. And then, so basically this was a typical type of a room that we see in especially the high-rise buildings. It was very similar to the room that I am. And these are certain assumptions behind the study. We have a little bit of a limited time. This was originally a 2 hours presentation. Right now it's 40 minutes. But for those of you who are interested, this paper is already published and available in ASHRAE website. For those of you who would like, you can find it on the website with all the assumptions behind that. But now let's go to the result. This is the result of that study, and I want to hold that slide right there, and I want you to look at it, and we have some discussions on that. We are looking at the glass temperature from here, from this frame, all the way to the top. Blue corresponds to double glaze with 2 low E, surface 2 and surface 4. Green corresponds to double glaze with 1 low E. And the red corresponds to triple glaze with 2 low E. This is the dew point of indoor air at 30% RH. This is the dew point of the indoor air at 50% RH, and this is at 70% RH. What catches your eye the most when you look at this graph? Anybody, doesn't matter, doesn't have to be right, just say something. Yes. Goes down, you mean, yes? Yes, exactly. So one of the things, that's a good observation. When you look at, so the red correspond, and there's something I want to bring up here, but the red correspond to the central part of the glass. The blue corresponds to the bottom edge of the glass, from the frame up to a certain distance up, and we're going to get to that distance in a minute. And the green is the top edge. You look at the temperature, you will see the temperature when you're talking about the center part is more or less uniform. But when it comes to the edge, all of a sudden it changes sharply. And we already know that, but this is the whole point. This is a typical double-glazed single lowy that we see out there. By adding additional lowy on surface number 4, we are cutting all of that safe zone. Which used to be forgiving to lack of perfection. In other words, in this case, the edge of the glass is 2.2 and minus 0.4, all the way 8.6 to 3.9. This region, and something else must happen here, this region is bigger than this region, which was another finding of this study. All of us are familiar with the edge distance. How much is the edge distance in the 2.5, 60? 2.5 inches. Well, it found out actually that 2.5 inches, it's only valid for the top. For the bottom is actually 5.5 inches because the cold air sinks warm air up. And when I was presenting this last year in US, the developer of a term software from Berkeley Lab were sitting right and they were presenting right after me. And they said, yes, Hamid, we found the same thing. That is why when it comes to condensation analysis on term, 6 inches being added. The model is based on 6 inch. Why? Because 2.5 inches doesn't capture all of that. And that was very interesting. This is something that when you start to look at how the heat flows inside the room, you start to see that. And obviously, this makes sense. Whenever the condensation happens, where do you guys see it most? At the bottom, and you start to see, and then gradually goes to the side, and then you start, so it shows up at the bottom. So the highest indoor RH before condensation forms at the bottom of the glass is 24% for the case of double glazed with 2 lowy, 29% double glazed with 1 lowy, and 41% RH for triple glazed with 2 lowy. And just for those of you, I chose the best warm edge spacer you can find in the market. I didn't go with even a stainless steel or something else so that that edge start to become cold. If you choose something even more, lower performing than this, you start to get even lower temperature. And these are the limit of 100%. And in our classes, I always tell the students, don't aim for 100%. 100% is already too late. What would be the safe RH level we need to aim for? We generally would like not to go at the surface I'm talking about, at the edge. If it start to go above 80%, not in the center, when it gets to there, because the center is 30%, 40%, no problem. But as you get close to the cold surfaces, the temperature drops, the RH goes up. So what happens, as soon as you go above 80%, surfaces that are susceptible to mold can start to be impacted with that. And this is interesting. This is case 1 with 2 low E, case 2 with 1 low E. And take a look at here, and I just want to zoom it. Here you will see more of a yellowish haze, and here is less. And you take a look at the glass temperature. So here, in this case, the worm is actually penetrating through the glass. In this case, that's not happening. The heat is reflected. We already know that. But the point here is that this one, the cold air sinking impact of the cold air can be seen, and the impact that it has. And this is very interesting. Take a look at this one. This shows the speed and direction of the heat flow. This is for the radiant floor heating. This is your wall, and this is your window. In the case of the double glaze with a single low E, something that we have been used, the heat goes up, complete the cycle at the ceiling, and then it starts to move this way. Take a look at here. The heat goes up. It doesn't finish the cycle. It comes back, and it somehow gets very excited to get all the way to the window. Why? Because the window is colder. The heat, this whole movement is based on now the glass is colder. So for equalization, that's the whole purpose of how the planet works when it comes to climate and wind from warm to cold. So when we have, and maybe this one can show it a little better, take a look at this versus this and this. This is double glazed with 2 low E. This is double glazed with 1 low E. This is triple glazed with 2 low E. This shows the speed of the air at the bottom. This one 0.27, this one 0.23, this one 0.19. The one with double glaze, because it's colder and because the delta T now is increased, is starting to have a more of a draft happening. Someone has studied this in 2018 when he also raised this concern, punched this into the thermal comfort of ASHRAE 55, and it says because the speed is going to be increased, the ankle draft thermal comfort criteria of ASHRAE 55 is not going to be met. Of course, we are low, and nobody look at that. The thermal comfort doesn't seem to be that important. We're so focused on energy star, and which is good, by the way, but all the energy efficiency and all the R value, air tightness, which is great. These are great, but at the end of the day, if the owners sit in a house, live in a house that is not comfortable, we haven't achieved our goals. And I'm going to touch on that a little more later on. So next steps of this study, as I mentioned, beyond CFD is going to have experimental and 36 scenarios for thermal comfort, 36 scenarios for condensation resistant, and all of that. But there is something that I want to touch for those of people who may have been, because there hasn't been any study on this, to really understand how this interior low-E coating is actually impacting. And what I found is that whenever there is a condensation, the owner called the homeowner, the window manufacturer, there's always find a way. Okay, so you have a blinds. Yes, blind is an issue, but there is no blind in this case. Okay, the heat registers are not supplying heat. The problem is your HVAC. The problem is this, that. And at the end of the day, I find that, lower your RH. The problem is RH. I feel that the end users don't have anywhere to go. It's because with this type of solution, make it less forgiving to the lack of perfection. In other words, energy efficiency solution, if I want to leave you with one message or key message, any energy efficiency solution that result in lowering the temperature of the wall or the roof or the glass, lowering that, it's not a holistic solution. Because that impacts not only the condensation resistant, Guys, this is very interesting so some of the discussion I have with HVAC contractors. There's always this question, and you guys know why we install the baseboard heaters or heat register of the furnace right under the windows, especially on the big curtain walls, window walls. Why? First of all, when you look at that, that doesn't make sense. We know the R value of the whole window and the door is almost R3, R4. Yes?
Not on, oh, there. One thing that I've found for decades has been ignored is the effect.
Can you speak a bit loud?
Sorry, one thing that I found for decades has been ignored, particularly affecting larger sealed units, is when the temperature changes, the center gap on the glass can also change. Did you take that? I know you took into account thermal things that a lot of people have been ignoring. Did you take into account that potential of the effect of the insulation value by the gap narrowing between the glass as air shrinks?
No. You mean the change in the glass width?
Yeah, that the glass in a larger sealed unit comes together when the air inside shrinks from being colder.
No. Okay. This was case by case. Basically, this was only specifically looking at the impact, but that can potentially be looked at. No, this is not in this one. So basically, I was just continuing, sorry, when you ask yourself, why do we install those heat registers under the window? We know the total R value of a curtain wall or window wall on a high-rise building. When you add the addition, the mullions, the coupler, all of that, probably R2, R3, all of the connections when you add it. So why do we put the heat sources there? It's the least path of heat resistance. The heat is going to escape. How that's going to be energy efficient, high-performance solution? But there is a reason we do that, because the windows were cold. We have to do that. We are actively supplying heat so that we raise the temperature of the window, so that the condensation resistance go up, so also that the thermal comfort be improved by reducing the net radiation heat exchange. We already know the windows are cold. Why are we making them colder? And that's why when you look at the triple glaze, one of the advantage of the triple glaze, and I'm not saying that I said at the beginning that triple glaze had its own challenges too, but the point here is that it's not just about energy efficiency. When I talk to some colleagues, HVAC colleagues, they love it because it reduces the HVAC load. You don't need to have any of the registers on the surrounding anymore because the temperature is passively heated. The temperature is already warm enough on its own. You don't need to actively blow heat to it to get up. You don't need to mask the symptoms. It's already warm enough, so the heat can be moved towards the center. Now, it's not finalized yet, but let me just share with you something that we have found on the thermal comfort analysis. And this is for those of you who work, architects. Do we have any architects in these rooms, in this group? Architects that work in this curtain wall system, window wall system. What's going to happen is that the heat goes and reflected to the center. The center gets warm, but the 2 feet, 3 feet perimeter, it stays cold. So all of a sudden we have a warm temperature on the center, but at the edge it started to. How is that holistic? Advising the homeowners to lower the RH is not it's not right. This is from another case study we are involved in Prince George. And look at the response of the window manufacturer. And by the way, the temperature wasn't minus 25, minus 35. Yes, please know condensation is very much normal. Have you tried turning the humidity down to 15%? Or have you tried leaving your house, maybe go to Mexico, or maybe don't even live in Canada when it's cold? What type of response is that? We're supposed to come up with assemblies that manage to provide the safe RH level for the occupants, 30 to 55%. We cannot tell the occupants bring it down because my windows or my walls or my roof cannot make it work, and then we will be happy that we have an energy efficient house. Doesn't mean anything, and that's why at the end I would like to bring this up. There is a misconception out there. When I talk to people, they say net zero, Hamid, a step code, step 5. All of these are great, and I say why? They said, oh, it's because it's comfortable, because it's durable, because of this. I said, no, that's wrong. The two are not equivalent. Yes, a high-performance house or a building by default become an energy-efficient building. But the opposite is not correct. Let me give you an analogy that may resonate. Let's say you want to we're going to achieve weight loss reduction. Let's say you want to lose weight. Well, I have to go through that recently, so it resonates with me. And let's say you have 10 diet programs out there. All of them is going to promise you to lose weight after 4 months, let's say 15 pounds. And let's say they all achieve that. You lose that weight that you want. So when you look at them, all of them show the same number on the scale, weight scale. Now, question for you. Are all of them holistic? All these diet programs? Yes, they all achieve the weight loss that you desire, but some of them may start to cause detrimental impact for your body by cutting certain food, by cutting certain minerals, long-term impact on the body. And now if I ask you to tell me, define the healthy person, do you just define it by the weight? No, you look at the whole element, the soul, the mind, how patient that person is, how forgiving to the frank opposition and tolerance of different views, what type of mind, thinking goes to the mind. What about the whole testing of the body? The weight is just one specific thing. Same with the building. Energy efficiency, it's only one pillar out of many pillars that needs to be there to achieve a high performance in outcome. The key here is that we need to design high performance by default. They become energy efficient. Right now in BC, we are dealing with energy efficient houses that have several type of issues, which is not the topic of that. One is truss uplift. Too much insulation in the attic, the truss all of a sudden lifted up. Overheating. The people are using high solar heating coefficient so that they can have a low TEDI value. All of a sudden, step 4, step 5, people are getting baked inside the houses because there's not even proper exterior one. Now, it's a very good energy efficient one. We have moisture trap because of sandwich things. We are getting, and this is what another thing that I wanted, because in US hasn't been that much widespread. But in Canada, because we are a colder climate, we're starting to see more of this technology. And sometimes we can go back to the physics and minimize these risks. I wanted to bring this up to tell you that there are consequences to this practice. And that when it comes to, you guys only look at the window on its own, and that's great. But when it comes to a wall, and in combination of various heat sources, the picture completely different. And why is that important? Because surface film, that means that thing that you're adding here is the big portion of the total R value. You don't even see it. It's not even part of that. That's why that study is important. Thank you very much. That's the first part of the presentation. Yes?
So Raymond Roy with Guardian Glass. One of the questions, 2 points.
Yes.
So
and your name, Roy. Yes, Roy.
Yeah. Is that we're looking at a constant exterior temperature,
yes,
right? And the other part is, can you comment on elevations? You know, when you're talking about high solar heat gain and solar tuning of a building, that can also be taken into account also, correct?
Yes.
To where you would have a warmer surface. And are you only talking about the relative humidity and condensation formation at nighttime, where there is no sun present?
This is good question. This is at the night time. So we are talking about the situation that the solar is not present. All of this condensation analysis that is done outside is based on heat flow from inside to outside. When the sun comes into place, it's not that we are dealing with this water or concrete that absorbs a lot of heat and then it can be raised up. So we are talking about material that have lower solar heat absorption. So this is for the case that it's cloud, you don't get the sound, or typical thing that we actually are experiencing in many parts of Canada when we are experiencing cold winter. And these things keeps coming up. The condensation is showing up and everybody's trying to look at this, and that's why we started to look at that, because especially for those of you who get clear sky like Kelowna, the temperature may be -2, but the glass temperature can get to -6, even lower, because the clouds are great. In Vancouver, yeah, you may say, is that high risk in Vancouver? You can argue, well, the temperature doesn't go that cold. Vancouver is a little bit different. But certain part that they get clear sky, that radiation escape to the sky results in further lowering of the temperature. And I can talk for that because I have some experiments on that too, but we don't have time for it. Yes. Any other question on this one? Any comment? Thank you. Any comment? How many of you have used this technology? Perfect. Just see that it's not the solution, it's a solution that needs to be looked at case by case, that you really need to advise the homeowners and the owners that, because you saw the response of that manufacturer at the beginning, and when things, yeah, go ahead.
Just an additional comment about from Building Science Canada. They were talking about with the lower air exchanges.
Yes.
Right? What do they expect the humidity level to be in these homes that are a lot more airtight? Just along this, are they planning for that 30 to 55%? Or?
Yes, so we are reducing the unintentional openings through our building. In the old days, we were relying on the air leakage through the walls, through the roof. Turn on the fan, bathroom fans, it brings the air, and that was providing the ventilation and all of that. But as we start to tighten up these buildings, this is also very important for those of you who deal with existing buildings. You're replacing the buildings, they do some changes, all of a sudden the RH level goes up. And then they get a call, the manufacturer get a call. That's why, that's another thing. You're changing the window, you're making everything airtight, and all of a sudden you're not touching the ventilation system. On a retrofit, it's exceptionally important. That's why we always say, put some sort of making sure the outsiders comes in properly, not relying on that. So intentional opening through HRV, through whatever you want to do, so that we get that proper ventilation happening, so that we don't. That was one of the problems at the R2000 program at the beginning when it was launched. We started to see elevated one. This is exactly another thing. It's like our body. We start to add vitamin D too much. We started to get another problem in some part of our body. It cannot just add, oh, energy efficiency is good, let's change it. Once you change it, the other things changes like that too. That's why we need to go stand up and look at how this change it's impacting. The key point here is any solution that reduces the temperature, the surface temperature of the envelope assemblies exposed to occupants is not holistic. And that's why we can learn from the lessons from other places. Europeans paid a huge price of mistakes because of all of this non-holistic thinking. I go there on a regular basis to window shows, and this is the first time I'm here and trying to talking to them. And so it was the same thing. Everybody got excited about energy efficiency, which is great. Love it. We should stop this heat escape. We have the technologies, but not in a way that start to come and bite us. 5 years, 10 years from now, all of a sudden we have to deal with the problems. So just be aware that the risk is there. Any other questions?
Okay, round two.
Round two.
Until what time round two goes? 1:30.
Oh,
Right? You've
very,
got
1 hour almost.
55 minutes.
55 minutes. That brings us to the next case, which I'm very excited to share with you because this is very fresh. And especially for those of you who work with some European windows and doors, they have come up to our market. All of you are from Toronto, from this area, yes? And is that common to use the European-made imported windows here or mostly local ones? Mostly local ones, yes. Well, in BC, because of the change in thermal performance and the requirements, some of the local ones, well, we have some great local ones in our market that they offer good thermal performance, very good thermal performance, but generally the industries they still have to catch up. So a good portion of the European-made ones have come to our market, which is great. We can learn from them, but there is a catch, and I want to share that with you. So where's my pen? Okay, so we are talking about this project in Kamloops, a fully exterior insulated house. This was a building. Kamloops is a part of BC. The construction quality is on a low side. This was a builder who came to our workshop. He said, Hamid, I've been building for 30 years, 2x6 with the regular type of window. I feel that it's time for me to change. And so he decided to go with this fully insulated building on the outside. All the insulation on the roof is located on the outside. All the insulation of the wall is located on the outside. Inside, there is no insulation, no poly, nothing. Bone dry, exposed to the indoor heat. And the window strategy was based on moving the window out so that you can keep it aligned with the plane of thermal insulation. Again, for those of you in the window manufacturing, this is a great market down the road. We really need this. We really need this type of products that can be offered as part of your window package, because that can, right now, because of not having this type of products, it makes it hard for the builder to install that, and that's why they go back to some other solutions. This is another one when the 2x4, 2x4 insulation in between. There are various ways of doing that. Again, this was from a construction show that I went there, so these guys are just, they do it to the masonry or to the wood, they waterproof it and install that. So this is what we did on that job, all the insulation on the outside. And there is, for those of you interested, there is a webinar, recorded webinar on the Builder Association, which I went through a step-by-step of window detailing and all of that. It's not in the scope of this one, but I just wanted to tell you that the conductivity, all of the thermal performance, structural performance are there. So the manufacturer tells you where to install the vertical pieces to support, and eventually this is what you're going to end up. Sometimes you need those pieces, sometimes you don't, those vertical pieces. So by the time it finishes, we are looking at something like this. The exterior 5-inch mineral wool insulation in this case goes and butts against that insulation, everything. Because if you don't align the window and the insulation of the wall, you start to get some lateral heat flow. The heat flow through the least path of heat resistance, and that drops the temperature of the, the temperature at the transition. So this is just some background. Now, the issue is not about the window. This homeowner is very happy with the house, exceptionally happy with this, with the exception of one thing, and these are the sliding doors. There are 5 sliding doors, one in the master bedroom, one in the basement, and also another one in the basement, another one in right there in the basement. So 3 in the basement, 1 there, and 1 in the kitchen. Let me go another photo. This is the master bedroom. This is also one. I'll give you different views. We keep referring to that because I'm going to show you some videos about some smoke tests. So I really want you to know. So this is the daughter's room, we call it. This is the son's room. This is the recreation room. And then the other one. So again, this is, and 3 of them are 3-panel. 2 of them are double panel. And we don't have problem on a double panel wall. We have problem on the 3-panel ones. Now, obviously, this homeowner, before even involving any engineer on the job, they wanted floor-to-ceiling windows, you know what, sometimes 12 feet high. It's huge windows, and with the least amount of frame. And obviously, when you go with fiberglass or vinyl, because of that type of a span, you need to reinforce it, and all of a sudden, the frame all of a sudden becomes a bit bigger. So they decided to go with aluminum in order to have a 2-inch frame, because the glazing for them was the most important one. So I'm just giving you some background to see. So now when it comes to envelope detailing, before we start to share what the problem is, when it comes to envelope detailing, same approach was implemented. Making sure that there is a continuity of thermal plane between the wall and the insulation. So in this case, these products, this is not a typical EPS foam. This is like a rock when you touch it. So basically, this is, pay attention to this type of insulation. That's the XPS insulation under the slab. It's connected to this insulation. This was a mock-up. The builder was doing it for the first time. So first, there was a membrane was installed as a capillary break. Then this product got installed with additional waterproofing over that. Let me show you a 3D of that. First, the membrane, the thermal, the capillary break, so that the moisture from the concrete is not sucked up and gets absorbed by that material. And then the insulation, and then the door. So this is the total view. This is the structural thermal break. So basically, you don't just install the door right on the concrete or on a 2x8 or something. It's actually encapsulated in the insulation. Now, on the upper levels, that product was expensive, so we came up with a different way of doing that. Having insulation sandwich between two 2x4 or 2x6, and then wherever there was post coming from the mullions, they needed to be the very heavy ones, so they needed to be especially supported. So for those point loads, this material was used. All that balcony is not touching the whole thing. It's spaced away so that we can have, so all the deck and balconies We just tell, and this is becoming actually typical in BC, I don't know about here, for exterior insulated assembly, given that we know it's an assembly that is holistic when it comes to high performance. Why? Because it keeps the structure warm. This is one of the things. In old days, when I open these old buildings, I don't see problem. They leak like a sieve, but when we are the 80 years old, there's water. But when I look at the wood, and I have a specific presentation on that, again, online, you can watch. The wood is good, 80 years old, no problem. Yes, it's leaking, yes, moisture, there's no peel and stick, none of those sophisticated waterproofing, but the wood is in good condition. Why? Yeah, because the heat, we didn't care that much about heat loss. So there's not enough insulation, not enough air barrier, plus a lot of drying. Sun was able to come in, heat from the inside. So the wood was taking advantage. Now, by putting the insulation on the outside, we can achieve the same condition with the exception that we don't allow the heat goes out. We're still putting all that jacket on the outside, so the whole wood is exposed to 20 degrees. What's the age of that house? That building, 100 years, 200 years, 300 years, 400. It can go, what's the age of this table when you leave it in this room, this wood table? If you leave it inside, how long it can last? It's exposed to that warmth. And that was the whole mentality, that if we really want to achieve energy efficiency, since we're cutting on the heat is good from moisture management, but since we're cutting it, we have to cut it in such a way that our structure is not impacted. So that is why we had to work with the structural engineers to make sure they come up with some sort of a blocking so that we can achieve that continuity. All that continuity is being done. In this case, this is the rough openings. What you see here is expanding tape. How many of you have seen these products? Is it used here? These are the products, again, very widely used in Europe. These are vapor open tapes. You put it around the door. Once you install it, after 2 hours, expands and nicely insulates. That's very important, especially for Prince Joe. Not a spray foam. I'm not talking about foam or any of those things that I'm not sure about here, but over there in the place that I practice, because of the shrinkage and all of that, cracks and associated moisture trap, we don't like that. We like to have products that allow for drying. In other words, we like to have forgiveness for lack of perfection. Perfection does, as a person that before I become an engineer, I used to build houses, so I come from that practice. And whenever engineers come to me and show me this perfect solution, I was always frustrated. And in fact, that was the reason I chose to come to engineering, because I said, you know what? We need to come with solution that will be able to work in not ideal condition. If you have these fine lines that the builder must ensure that the construction doesn't get wet, it get wet. In Vancouver, we get a lot of rain on a regular basis. Things get wet. We cannot assume that they don't get there, no matter what they do. So we need to come up with solution that wetness can be allowed. That is why this is the background. In this case, especially in Prince George and some cold, that age, it's not given that much of an attention. Sometimes we leave it open, sometimes we do backyard and caulk, sometimes we just put some fiberglass or mineral wool, some people spray foam. These products, you just put it there around, and it's very nice. It goes and it's nicely sealed. Seal around that edge. Okay, so I think I'm talking too much. Yes, and then once the slider is installed, then the air seal is happening by high performance tape or backyard and caulk. High performance tape sealing it from the air seal is important. Air and vapor seal, sealing it from the door to the air barrier of the wall. Let me show you a photo of what I mean. So this is that detail. This is the expanding tape that I'm talking about. You can just go with the backyard, with the caulking. You don't need a backyard. This serves as a backyard. Or you can just do the tape. I showed both of them that you can see. Some people like tape better because you can see. Some people, the caulking better. It's really options. So right now, this comes at the side. When it comes to the bottom, this owner didn't want the 4-inch step. We always have a 4-inch step, or he wants the flush from the inside outside, same way that he saw in Europe. So that's why we ask for a fat bit of caulking. So we had a gap underneath and add a bit of caulking at the bottom. You see how thick is that, as well as the tape. So in other words, when you look at this, I ask for some sort of a back dam, a 2x4, so that we sink the door down, and then have that caulking plus the tape. In other words, I always say, don't tell people you cannot achieve, or don't tell architects, no, you cannot. Yes, we can do that. We can do whatever you want, but we need to do something about it. If you want to do this type of high-end stuff, don't just assume things gonna go work. If you're dealing with buildings have a lot of steel beam and frame, be careful. I'm dealing with another independent third-party reviewer right now on a window manufacturer in BC that the windows are condensing, and it's because how it's connected to the steel beam and column. There was no thermal break. They just connected it, and the steel gets cold, and all of a sudden it transferred that. So all of this is important. So this is the end, in other words. Now, you may say, okay, Hamid, you talked a lot. What's the issue? The owner reported condensation on December 20th, last December and this January. The owner said, you know what, on these two sliders, Hamid, on these two sliders, we are getting condensation and sometimes frost all around here, as well as at the bottom here. When the temperature gets to -8, which is nothing when we talk about cam loops, BC. And he was surprised because he paid a lot of money for these, and these are supposed to be highly thermal efficient. We're talking about U value of less than 1 for a triple glazed, fully thermally broken aluminum door. We are not talking about U value of, so this is 0.9 almost watt per square meter per K. We're not talking, so, and I show you how that looks like. So let me first show you, this is a fixed part. The slider goes this way. So this is the rail. So let me show you some. So this is the rail, and this is the fixed part. So this is the actual door, and there is a fixed one connected to that. And there is condensation. So let me show you what do I mean. And I don't know if you can quite see it or not, and I don't know if the video sounds, I'm sure, but I just want to show the owner is talking on this video. Just give me. Yeah, it sounds like I cannot have the sound, but basically, do you guys see that? He's basically saying, that's why you're hiding, all around. And he felt some draft, so even put some backer rod, and he tested it, and he said, it's all happening there. And again, we are not talking about a small amount of money here, and I can't discuss, but this was something that he was sold into, that this idea that this is going to perform well and up to, -25, -30. So the question is, then the owner said, so we already, sorry, I need to just, so now, let me show you the profile. Take a look, it's quite a sophisticated door. I worked with a lot of manufacturers across the globe. This is the first time that I had to really think to understand the system, because, so this detail is this one. This is the cross section. This one is this guy, this one is actual door. I just want to bring this one so that you can see. This one is this section. Take a look, so this is the insulation. Triple glaze, insulation. You see, it's a lot of insulation is placed into that. This is quite engineered system. A lot of attention to having proper thermal break. All these pink ones are thermal break. This one is this cut. We're gonna come back to this. This one is this one. This one is this part here. With the difference that when they send me the thermal modeling, they show complete glass, whereas in our case, we have a frame installed inside the frame. And this is also important. So in other words, we have some sort of a frame inside another frame. This one is this part here. And this one is the end. So owner reached out and asked for my opinion, and as soon as he said that, I said, you know what, I think I know what's going on, because last year, in January 2022, which this was the time of the construction, we had air tightness testing an infrared reading happening on this house. And when we were doing that, the house was depressured, means that the guy maintained a negative pressure, so that when I was looking at the reading, I saw these kind of hazes. Whenever you do IR camera and you start to see this cloud, that's the sign of air leakage. If you see solid line, that's the sign of thermal breaches. So that means it's a piece of metal or something, and I'm gonna show you how to figure that out. So in this case, this one is basement. These ones, look at how it was like, and then the master bedroom, look at all of that. I remember last year we said to 20, well, this is leaking, and you could see it's leaking actually. And he said, well, it's not being adjusted, it's going to be adjusted. So then, and I explained that air leakage is very important because all of these thermal analysis you get from companies to do for you U value, and we are getting so detailed about the U value calculation. It really bypassed if you have air leakage. Imagine you have a very good insulated jacket. If you unzip it, that insulation that is offered by the jacket is bypassed. None of these, all of these U values that you get is based on the assumption of zero air leakage. Air leakage is not part of the model. If you end up getting air leakage, and what type of air leakage? Infiltration, exfiltration, we're going to talk about that. So that is what, and then but the owner said, well, I'm going to object you. If you're telling me that air leakage is the problem, why I don't have a problem on the master bedroom? It's the same type of a door. I have a same type of a door. How come I don't have it on the second floor? Why is it only at the basement? Why? Yes. Can you come forward? It's okay. It's warm above, okay? But in this case, we are talking about quite a thermally efficient envelope. The temperature changes really between top and bottom. We're not talking about too much of a temperature difference. That's the benefit of high performance building. But you are onto something. Yes? Overhang. Oh. What else? Okay. So then I said to the owner, you also have problem on the master bedroom due to air leakage. You don't just see it. Let me tell you why. And he said, why? Well, I said, well, I need to explain a little bit of physics. Very simple. When you look at these new buildings with no chimney, there is a plane somewhere in the center of the first floor that above that, the warm indoor air wants to go out, exfiltration. Below that, the cold outdoor air wants to come in, stack effect. So the combination of the mechanical and a stack effect and wind generally, if you have a chimney, it's a little bit different, the old houses. So warm air wants to go up, so you went on to warm air goes up, wants to go out, cold air is gonna come down. So what I was explaining to the owner was that in the case of the basement, the cold air from the outside wants to come in. We have an emergency alert on this case study. So basically, on the basement, guys, pay attention to this one. On the basement, this is the important part. On the basement, sorry, my handwriting is not very clear. So the cold air wants to come in, and as it comes in, bypasses the air tightness, the gasket, it comes in touch with the aluminum. What's the thermal conductivity of aluminum? 160 watt per meter per cubic meter. So it started to make that cold. So all of a sudden, this temperature become cold. So the indoor air start to see that cold air and start to cause condensation. On the second floor is different. Warm air wants to go out, and so when it goes out, it gets cold. So I told him, you also have a problem, but you need to open the door to see the problem. And this was, I was just on the FaceTime. And I said, can you open the door and see what the problem is? And I was on the FaceTime. So again, we don't hear the owner. The owner, and I wished you could hear it, but so he's opening it. You saw the ice and things. So we had ice and we have ice. So this is inside. The warm air from the inside bypass the gasket and condense inside from all around. The door, you cannot even open it. You don't hear the sound here. He wants to open it and the whole ice breaks and then damages the gasket. So then I asked him to send another video. You see, this is not snowing. This is that ice that is right there, warm. And again, in the basement is different. Outside, and this is interesting, no? How the air leakage behaves in different parts and how all of these come together and why it's important we look at it holistically. Outside there in the basement comes in, cold air comes and it makes that aluminum cold. If it was fiberglass or vinyl, it would have not done the same thing because the conductivity is much lower. But in this case, we're dealing with aluminum. It's bypassing all of that thermal break. So now let me show you another video. This is also a little bit more clear. So this was another one. And this guy is... And then he said, oh, that makes sense. But then I said, we need to prove this hypothesis. I'm going to do something to show you this is what I'm just explaining. It actually makes sense. So as the next step, I asked that let's hire the same guy who did the air tightness test, but this time we're going to ask him not to use a fan. No fan whatsoever. Just come there and do what? Do a smoke test. I was in Vancouver, in my car, doing a FaceTime, and this is the basement doors. The guy stand on the outside. When he did the smoke, a smoke was coming in. But when it was doing it from the inside, the smoke was not going out. Let me show you the video. So we are talking about, which video is that one? So there we go. So this is the first video. Right now in the basement, he is trying to blowing the smoke. It doesn't go. The air is actually holding it inside. It doesn't go anywhere. But I told him, can you go outside now and repeat the same thing? So what happened? Going outside, it leads to this one. And you don't see the noise. So let me just move it a little bit to the... Just on the outside, no fan, nothing. This is just a normal operating condition. It's putting the smoke is coming in. Now I said, okay, let's do the same thing on the second floor now. What do you think is going to happen on the second floor? Now on the second floor, it was the opposite. And this is very interesting to see how air leakage manifests itself in different locations. So in this case, the energy advisor is standing outside and just with no pressure, nothing. We're just... Imagine this would be a warm, indoor, humid air coming out when you have a cold outside. What's going to happen to that? Turns into ice and it stays in the door system. The owner opens it, it's going to impact the gasket. Let me show you another video. Do you see the smoke? It's coming. So this was actually proven. That hypothesis, this is how we need to, interesting to see how all of this comes into play. So, and this was very difficult process because originally dealing with this manufacturer, oh no, you know, who are you questioning our system? It's been under development for 20 years. You guys are behind of us. So we had to be quite a persistence and perseverance to go through all of this from a physical standpoint to build up the case. And then I wasn't done with that. I said, let's do an IR camera again. Let's do infrared camera again. And here on the basement, when the cold air comes in, you see again the smoke, the cloud. When you go on the second floor, you don't see it. In other words, just pay attention. This is one of the best slides of this whole presentation. Same location on the master bedroom. This was done 2022 with depressurization, meaning the inside was, so the pressure, so the inside, it was maintained on a negative pressure. Outside air was coming in, you see it on the master bedroom seal. This 1 year after, no pressure, just the warm air going out on the second floor. You don't see any of those hazes. You'll see it on the outside. And this is very good, especially for you guys having this type of thing and show up when they do the airtight. I don't know if this is a law here to do this, but over there, every house, every building needs to go through this. So it's very good for you guys to get to understanding of your system. So then the question was, why are they leaking? This is supposed to be a high performance door, came from Europe. Why are they leaking? Well, the window installers said, well, the gaskets were damaged during construction. You guys were not taking care of it, so these came and get damaged. And this is the builder response. They said, no, we only used one door. Out of all of these doors, we only use these doors for the workers. We closed these ones. And I really felt that the builder was, and it didn't have that technical thing to discuss it too, and I felt that they were putting unfair, they're treated unfairly. And I said, yeah, so I said, yeah, I was on during construction. I don't think that doors, and the homeowner said, we don't think that's the reason. But anyway, the window company said it's the gasket. The second one, they said the final door adjustment were supposed to be done by the builder. That means in the contract, you were supposed to do the final adjustment of these highly sophisticated doors. And I'm going to get onto that. This is very interesting. This is something that we need to be very careful, because right now we're seeing these European ones come here. So there's a high cost for the installation, but there's a high cost for the whole unit, but there's also 30 grand, 40 grand sometimes for the installation. And then the owner want to save the money, so then they let the carpenters do that. But these are highly sophisticated things. So if something goes wrong, then, you didn't want to pay for that 40 grand. So end user, all of a sudden, now you have to hire someone like me trying to figure out who is right, who is wrong. It's not serving the end user. So before I comment on this, I want to show you a step by step. These doors were put together on site. They couldn't fit inside the shipping container. And look at the part, and by the way, these are plywood. Exceptionally good thermal break made out of marine grade plywood. That's why they get such a low U value. And look at I just want to go through the slide to show you the level of the step. The seal piece goes, now you put the caulk in there before the jam piece goes on. Now you do the shims, very detailed installer by the way, and then you put these side pieces, the post and all of that. And now the top piece goes on top. Then expanding tapes goes around. I just want to show you the steps. I want to get to something. Now they're installed, lifting it up, putting it in place. Now this was the surround frame. It has a fixed and it has an operable. The fixed one by double-sided tape is placed inside the frame. And then before they place it, they put this expanding tape that I talked to you about it. They put it right there before they put that frame right inside. Same thing here. Now the fixed part of the door is placed inside. Then all the gaps are sealed with, insulated with backer rod. And I think this is something they do very well. I think here, I look at the shop drawings, we see a lot of openings. It's good to basically have some sort of insulation right there. And then this is the side. I just want to go through all the steps of installation on site. And then the gasket down there, and then another gasket. Look at all of these notes. I had to spend almost a month to study all of this because I wasn't there to understand. And then this corner piece and how that corner piece has to seal. It's just too many pieces are involved into that. Just imagine this is built, and back to the part 5 test that Terry was mentioning. So I'm going to talk about that as well. So now we have this layer, and then the thermal break, and then the other part. Look at how many parts. Look at all the attention that has to be given to these corners, all of these notes. And now they install the pressure plate with insulation at the back, all of these pieces, and then you need 5-6 guys to lift this whole thing up. In other words, is that fair to expect the builder to install this door or even adjust it? In fact, and that is why originally this was the email I sent in 2021. When they told me, I said, well, we're going to stay. I'm not going to allow this, although I'm not in a position to tell the builder how to deal with the subcontractor, in this case, door manufacturer. But I raised the flag that This is very risky. If you want to save that, and if something goes wrong, who's responsible? The door company can say, well, you didn't follow this installation. Even their installer had all sort of problem following it up. And that is why when you look at this one, especially, I just want to bring it to your attention. Look at this part, the air barrier. What this is inside, this is outside. There is a bit of a flap, which in reality looks like this. And this was supposed to do your air barrier. I actually don't like this one. I was expecting something to go and lock into something. So this is just a not 90 degree, 85 degree, a little bit of a flap. So imagine if the door is not properly adjusted. You get the air from inside all the way going to the outside. It's a highly thermally performance. It's great when it comes to thermal performance. But it sounds like when it comes to air leakage, I'm starting to realize that some work needs to be done on their side. So that is why I was mentioning that. Now, we understood that there is an air leakage, and now the question is that who was responsible? But the question is that, was there other reasons? Were there other contributing reasons? And yes, blinds. These two basement doors, they were provided with a double blind system. Again, I haven't seen it. So not only one here, but one on top of it. So 4-inch, 6-inch, almost 10-inch away. And the one look at the blinds, and the one in the master bedroom also had some sort of a blind like that. But then the other two doors, the single door, the double panel doors, that didn't have a problem, they didn't have the blind. And this is why we emphasize, and I think, although they also had air leakage. Why? Well, we knew about this. It's already documented in ASHA handbook before even I started my career, that blind like this inhibit the heat reaching to the glass. In fact, if this was not a triple glazed door, thermally broken, the whole thing was sweat, full sweat. We are lucky that it's triple glazed. And in order to test that, on 3 days, that the temperature got to minus 14, 16, and 20, from 6 p.m. to 7 a.m., I asked the owner for one of the rooms, keep all the blinds down, for the other rooms, keep the blinds up to see in the morning what happened. And he said, I saw around 50, 60% improvement. We still had condensation, but it was less. You see how all these pieces coming together? That's why I remember I went to a doctor, I said, I keep getting back pain. And it was 10 years ago. He said, well, you used to be swimming competitively. You seem to have a strong back. I think something is wrong with your mind. Probably you need to get rid of need to forgive people if someone bothers you. And really, at the time, I had this problem of not letting go easily. And he was right. I started to work on that, and my back pain went away. I didn't need to go to chiropractor anymore. And this is how this whole thing is needed to have the proper, some people are laughing, but this is true. Some of our problems and pains is really come from other sources. Buildings are also the same. We see condensation, we think the problem is the window, or the problem is RH, or no, we need to, that's why even in the, doctors are promoting a lot of integrated health. It's the same thing with the building. Someone mentioned about the air tightening, and then the RH level goes down and all of that. And then that was not enough. In order to prove that, I asked the door manufacturer, and that was very difficult, to give me a condensation analysis. And they gave it to me. In Europe, they do 20 out inside, minus 10 outside. We do 21 and minus 18, and I have covered that in a long time. Why it is like that? That's not the point here. But the point here is that I said, okay, the dew point of the indoor air in that house was 21, very similar to 20. It's around 5 degrees. I told them to give me an isotherm. If the inside is 20 and outside is minus 10, show me the 5 degree line. And I want you to pay attention. Let me start from here. Show me the 5 degree line. Look at the 5 degree line. When it comes to here, it's good. This is warm. This is warm. But look at here, the 5 degree line. Every time I look at these slides, I see it. See? It touches that gasket. The plane of condensation is already exposed to the inside. In other words, warm indoor air can easily reach there, and if it gets there at -10 and below that, condensation happens even if you don't have air leakage. Take a look at here. How the blue, we really want to see cold on that side. As soon as you start to see the cold coming closer to the inside, we get concerned. And here, all of a sudden, that is touching and cutting through that gasket. That is without even having an air leakage. And that is why it's important that we don't have a blind to make sure that heat easily get there. And that is why when it comes to condensation, we don't look at condensation. How many homeowners or builder ask you to provide result of the condensation resistant? Almost none. We are so focused on solar heat gain coefficient, visual transmittance, and U value. Yes, and for the U value, as long as you know how to do this. So we have center of glass, and we have the edge, and then we have the frame. So U frame multiply area of the frame plus U glass multiply area of glass plus U edge multiply area of edge dividing by the total area, and that gives you your U value. Very simple formula. But when it comes to condensation, the total U value is not important. The U value of individual part is important. The condensation resistance is defined by the thermal performance of its weakest one, which is, in this case, the edges. And that's why it is important that we will be able to see that. So what now? This is interesting. The remedial, so they accepted that there is a problem, but they still said the builder needs to pay for that. And listen, this is the interesting part and how it was unfolded. So I recommended step 1, replace the door gasket. Everybody was on argument that the doors has to be removed, just the slider, not the whole frame, and replace all the gaskets. Do the smoke test and IR camera while pressurizing and depressurizing the house. Bring the same guy here, pressurize and depressurize, and see how it works. Why? Because we didn't want to just do on-site Part 5 compliance test, ASTM1, and if it fails, then it was difficult to figure it out. Step 3, on-site testing for water and air. Water is done a lot. Air, we don't have too many companies do that. In fact, it's rarely you can find airtightness test of on-site airtightness test. Have you guys seen it? It's rarely done. Water is done. Yes, we put the rain racks, we put the spray, and then we remove the air, and then we do it. But when it comes to air, it sounds like we don't care that much, but it sounds like, now this study even emphasized, I learned a lot from this, that how air leakage, it actually have an impact on this whole performance. And step 4, utilize only 1 blind, not 2, and keep it 1 feet up so that the heat gets there. Now, this is interesting. September 25th to 29th, which was just over a month ago, they went on site to replace it. I went to Kamloops and I stayed there for 4 nights because the owner wanted me to present to document these things. And this is very interesting. When they open it up, they realize it's more than just the gasket. Not only the gasket had to be removed, but this whole mechanism at the corner. By the way, this is not lift and a slide one. I think I misinformed you. Yeah, it's not like that. But also I started to see they're starting to cut something. I said, why are you cutting the bottom of the frame? This is not part of the gasket. Well, it sounds like it was a little bit high. And then they start to realize that this piece needs to be cut back. So they put it on a table. So all of a sudden we are rebuilding this whole. Then they remove this panel and they talked to on the FaceTime with Europe, and they added these foam and caulking there because the corners was a little bit of a problem. Then they started to find out this is Boeing, and I think that a structural test of NAFs is important. The frame was started to go this way. So now they started to drill and put some fastening to connect that to the thermal break of the fixed system. You see, I said, well, this is not just a gasket problem. It sounds like we have beyond that. And then this backer rod that you see here, they said they are doing this type of a product which is providing better insulating value. And once it was done, we were ready to do the airtightness. Bring the guy to do the airtightness test. But they said before we bring it, we want to do our own test. Just have a blower at the outside and just blow some air. This is just something for them to understand. So, and I want to show you how much of an improvement it made, all of these changes. And just And the last part is interesting to show. So you don't hear this, but it's very interesting. This is the blower. Again, this is not an ASTM test. This is just the window company said, before those guys come and I look bad, I want to do my own thing. So corners had this problem. But beyond the corners, we didn't have the problem. When you see, before the air was leaking from that. Now look at it. This was quite a pressure. Air was, again, this was just subjective. This was not exact. See how it helped? All of this. So they were there for 4 days doing that. And they said, yes, there was more problems. So on site, they mentioned we have to pay for this, apparently, not the builder. But you see how the persistent, but when it got to the corner again, the corner, see, it's all bit, all of that was leaking before. You saw the videos. But now when it gets to those corners and the mechanism of the corners, this led to this email that I got 4 days ago from Europe, that I just want you to read this. They're acknowledging that there is a problem, that we're gonna build the complete one in our manufacturing and do complete tests on them, and then send someone from Europe to install it. If not, give you a new sliding door, and if a sliding door doesn't work, we give you a swing door, or we fix it completely for you. It took around 8 from January till now to get to that. It's not easy until you really stick to principle without getting emotion, no blaming, no pointing, stick to facts. And this is actually very interesting. But then the here is that everybody knows this was not a NAF certified. Well, that was not the case. They had the NAF certification for this configuration. Somehow they felt this would apply to this one. If you have the double one tested, automatically the third one would be that, because they said the mullions are the same. And that was the no. When you have a single one, when you have a double one side closes against the wall. You only have dealing with one critical area. But once you have a single, three panel one, you have 2 weak points on either side. It's completely different. Probably you can apply the 3 panel to 2 panel, but not 2 panel to 3 panel. You guys are more expert on these things than us. Now the question is this though, and that brings us to something. You see how I just wanted to show these 2 case studies. My passion is about end users experience and durability. And all of our projects are ultra energy efficient. But we don't do it just for the sake of meeting some metrics or getting some certification, but rather how can it be done holistically. Look at how an ultra thermally efficient door, it's performing weakly when it comes to air leakage, and how that is impacting the overall condensation. Now the question for you is that, well, so this was factored in site installed. But now as I was studying this, I found something I shared with Terry. I said, why in NAFs, the air tightness test is based on area? Why all of a sudden? It used to be based on linear feet. At A440, what was that, a standard CSA? Why all of a sudden? And I know why, because when it comes to energy loss, area is good. We can convert it to area, heat loss, all of that. But the reality is that, imagine I have a sliders with 3 panel and a slider with 2 panels, same area. The reality is that not that much of a air leakage is happening on the fixed part. So even if it's NASP certified, doesn't mean it's a good or not. I think we have to have some sort of a study relating the air leakage to moisture management, because right now, again, we are only caring about air leakage as far as energy. Oh, if it's less than this liter per second per meter, whatever, so this good. Yes, but what about this issue that I just talked about? If we're gonna have, maybe the next metrics that needs to be looked at is that if you're building in somewhere cold, that the outdoor temperature drops to that much, the air tightness has become even more important than in Vancouver. Who cares in Vancouver? This air leakage, it would have not caused any problem. Yes, it caused a problem for sound, acoustic, it caused a problem for dust, it caused a problem for draft, but it doesn't cause this condensation problem because the temperature rarely drops below -10 where this was happening. Make sense? So this is something, again, sorry if I, well, there is more to that, but again, I hope that there would be an opportunity if you're interested to talk a little more on these things. But the whole point is that let's embrace high performance solutions that are holistic so that we can achieve proper durable buildings and a good comfort for the occupants. Thank you very much. Thanks a lot.
Questions, anybody? That was a lot of information. You're one passionate fellow.
Thank you.
Great presentation. That was
Thank you.
really good. So questions, no? Okay, thanks very much.
Thank you very much. Thanks for coming. Appreciate it.